Well, regarding Sheliak instruments, it was I didn't like this year, in fact, like a lot of people, of course. I didn't like it, but at the end, we had from business standpoint, we had a quite good activity, so it was not too bad. It is not an outstanding year, of course, but it was not too bad. So we are still here. We are still motivated. We have still a lot of projects, and well, currently, you know that we're working on the new instrument, the UVEX, and we will deliver the first unit very soon. And this is a very interesting project. And so we had a good activity. And you know that for me, it's very important that we are doing spectroscopy, and spectroscopy is quite technical. It's a technical activity, but it is very important to keep in mind always that if we do that, it is to do science behind. And it's really a pleasure today to have François Teyssier here to talk about this this nova that appeared a few months ago in the sky, and this is very important that this is a very good example of how we can join the technique and the science. And well, you know, we already had this talk last week in French, so I know a little bit what it will be about, and I can tell you it is very interesting, and we had a very good feedbacks last week. Okay, so well, as Olivier said, we'll look at the chat and we'll take the questions if you need, and also François, we say that maybe I can either interrupt you or help you for the English if you want. So
yeah.
Be comfortable, and that's it. So thank you very much, François. Do not hesitate, everybody, to ask questions through the chat, and let's have a good talk.
Good. I'm sharing my screen.
Yes, we can see it. So
Good. Is it correct?
Now yes, it is perfect. It is in full screen now. Yeah.
Perfect. So hello everybody. I propose a workshop about Novae. François Cochard, as he said, will keep the micro open in order to corrige my English pronunciation. Okay. I propose the agenda. First, introduction to the theory of Novae. And at the end of the presentation, if you have questions, I try to answer if possible. Thus, for about 1 hour. After, I propose a break of about 5 minutes. And after, the second part will be a more interactive talk, discussion between us about the practical study of the spectra of Nova Persei 2020. I use for that presentation, PowerPoint, but also I will show how we can use various softwares to study the spectrum. The spectroscopy of Novae began with a first spectra of nova obtained by William and Margaret Huggins in 1866. At the beginning of the 20th century, Gunmark proposed a great debate and the classification of the new stars in 3 categories: supernovae, classical novae, and dwarf novae. At the beginning of the 20th century, especially McLaughlin produced number of publications and proposed a systematic study of the bright novae of the first part of the 20th century. The bright nova, Hercules 1936, has been an important moment with the first publication of the spectra secured by several observatories. Here, I show the spectral atlas. If you can see, the spectral atlas is very nice because you have many spectra of the nova observed by these observatories. In 1957, Cecilia Payne-Gaspocchi published Galactic Novae, the first book about novae. About the theory, this is at the mid of the 20th century that Walker studied the nova Hercules 1934, DQ Hercules, and established that it is a binary star. Kraft produced the following hypothesis: all cataclysmic stars are binaries first. Second, the novae are produced by a nuclear explosion at the surface of the white dwarf. Here is the classical nova Delphini 2013 and the luminosity curve in V band of this nova, which this luminosity curve is very typical of a nova, with a very fast rise, a first decline, a second decline, and after the fading of the star. McLaughlin produced a typical luminosity curve of observed novae, with especially a pre-maximum. Do you see my arrow on the screen?
Yes, yes, yes.
Yes,
Yeah.
okay. With a pre-maximum alt, what is named a final rise, an early decline from about 2 magnitudes from the maximum luminosity, and a transition phase, which can be smooth with oscillations or a very deep. This is the light curve observed in nova Delphini 2013. This is now known as the formation of dust at a certain moment of the decline of the nova, and these are oscillations, and we'll come back on the oscillations about the study of Nova Persei 2020. Payne-Gaspocchi introduced the notion of speed classes for the nova, with the classification from very fast to very slow novae, and introduced a time scale with the decline of the magnitude of 2 magnitudes with T2 and the decline of 3 magnitudes as T3. And there's this method to for the classification of nova is still in use, in usage. One very important point, which was known by the precursors, such as Cecilia Payne-Gaspochin or McLaughlin, is that during a nova event, the bolometric luminosity is constant. When we see the visual luminosity declining, we have in other ranges of the spectrum, in UV, in IR, in radio, in X waves, new maxima. And globally, along all the nova event, the global luminosity, say the bolometric luminosity, is constant. From various studies of nova events, it has been observed that we have in the ejecta an enhancement of the abundance of the metals. It has all the ionic species, all the atomic species over oxygen. Description of the evolution of an outburst through spectroscopy. Near maximum light luminosity, we have a blue continuum. We have number of metallic lines in absorption, faint emissions, notably of Balmer lines, but also iron lines, which shows P Cygni profiles. During the transition phase, this is the dose point of the luminosity curve of Nova Delphini 2013, we observe a fading of the continuum, an increase of the emission lines, fading of the absorptions, and many lines of nitrogen, oxygen, helium appears, but also at certain moment of the development of the spectrum, the apparition of the so-called forbidden lines, such as in this example, oxygen, neutral oxygen forbidden line. In the nebular phase, the continuum fades a lot, and the forbidden lines can become very intense. Here's a spectrum of Nova Delphini obtained during the final decline, and here is O3 line, much more intense than H beta. McLaughlin has described the general changes of the spectrum with a scale from the maximum luminosity. And he has observed over 7 novae the variations on the spectrum of the spectrum. On this graph, we have the light curve of Nova Delphini 2013. And I show first in blue the absorption systems, which have been defined by McLaughlin as pre-maximum absorption, principal absorption, and Orion spectrum. McLaughlin has also worked on the emission lines and have defined that the oxygen line often appears about 2.5 magnitudes above the maximum line, followed by nitrogen flash, followed by helium flash, followed by O3 flash. There is an increase of the ionization level of the different emission lines. Here is an example of flux measurements on several lines of Nova Cygni 2014, and one can see sorry, an oxygen sequence from neutral oxygen, oxygen ionized one time, oxygen ionized two times, and we can see that while the oxygen ionized one time, O1, is declining, we have an increase of oxygen ionized one time, sorry, neutral, one times ionized and two times ionized, and the ionization of O3 happens while the oxygen one decreases. From high resolution spectra, we can observe the profiles of the lines. Here is an example of a Shell spectrum obtained by Christian Will on Nova Monocerotis 2012. And this is the oxygen 1 line. From this observation, Steve Shore, used a Monte Carlo method in order to build a theoretical profile of this line, and from this method, with this method, obtain a concept of the ejecta. We have also, not from amateur world, of course, images of the remnants of the Novae. Generally speaking, they are spherical, but oblates with a low eccentricity. They are often very clumpy, and sometimes we can see wings, lobes, and so on. This one, published by Shawa from observation with Hubble telescope, is very interesting because from the different blobs observed in the image, they have been able to deduce the radial velocity of the ejecta. Now, I go to the theory of the dwarf of the Novae outburst. Most of them are observed in cataclysmic stars. Cataclysmic star consists of two stars, a donor star, which is often a main sequence star of left type, often hem, so it is cool, it is red, and a white dwarf. The equation from the donor star forms an equation disk, but there are also a category of cataclysmic stars called polars, which harbor a very magnetic white dwarf in which there is no equation disk. The transfer of matter, sorry, I will correct, of course, the French words, is of solar composition. Essentially, the abundances are about the same that solar matter, with essentially hydrogen and helium. The two stars orbit in a very short period, a few hours. The distance from the white dwarf and the donor star is about 1 solar radius. The accumulation of matter in the equation disk, I launch the video. This is a model of equation from the donor star to the white dwarf. Here, the matter and the formation of the equation disk. When the matter accumulates in the equation disk, there is an increase of the viscosity, and we can observe sometimes a sharp increase of the temperature from about 5,000 degrees to 15,000 degrees. This is a thermal outburst. The amplitude can vary from 1, 2 magnitudes to 8 max. The frequency of such outbursts can be days to years, depending on the systems. And the duration is a few days. These events created by the increase of the velocity and the temperature of the equation disk are called dwarf nova outbursts. We can see the light curve of dwarf nova SS Cygni from AVSO database with the outbursts from magnitude 12 to magnitude 8 to 8.5. Each one is different and are very interesting to study. Last point, from photographies, images of the vicinity of cataclysmic stars, shapes of remnants of very old nova have been detected. This is an example. Another example with a very, very nice picture obtained in just at the beginning of the 20th century shows the nebulosities observed in GK Persei, which has been a very white nova. The main component to understand the nova phenomenon is the white dwarf, which is in fact the terminal phase of the stellar evolution for stars under 10 solar mass. There is no more thermonuclear reactions in this in the white dwarf. We consider that the material is cool in the thermodynamic sense. Is that in fact les noyaux, François, tu peux m'aider, noyau d'un atome.
Wow. Non.
Bon,
Nucleus.
Ah,
Thank you.
The nuclei of the atoms are frozen, in fact. They doesn't move. And the stability, in fact, of the white dwarf is secured by only the motion of the electrons. Depending on the mass.
François, white dwarf is it is written naine blanche. If you can show it, it is in French on the graph. So
yeah.
Just to show that white
I
dwarf
have some corrections here. Carbon with no E, oxygen. Yes, it will be corrected for the final.
No, I just wanted to say just show on the graph that white dwarf is naine blanche, and nebulous planetaire in France it is planetary nebula, and géant rouge on the graph is red giant.
Thank you. The white dwarf, depending on the mass of the star, can be formed essentially with carbon and oxygen and neon for the more massive progenitors. We can have also helium white dwarf. The mean mass of a white dwarf is about 0.6 solar masses. And I recall that if the mass of the white dwarf is above 1.4 solar masses, approximately, because it depends on several parameters, the white dwarf will
Rich.
To neutron star. Yeah. What is very special with this material is that if the mass of the white dwarf increases, the radius decreases. This is very uncommon. First, from several theoretical models, one can see that according to the mass of the white dwarf, from about 0.2 to 1.4 solar masses, the radius of the white dwarf declines from about 14 to 2,000 kilometers, the density increases by a very large factor, and the gravity follows from on a very large range. Thus, we have significant variations for the different physical quantities according to the mass. In our world, in the so-called normal matter, the gases follows, thank you, the perfect gas law. It is, if the temperature increases, the volume will increase. Of course, if the material can expand. In the degenerated matter, such as observed at the surface of the white dwarf, all the nuclei are frozen. Only the electrons maintain the structure of the white dwarf. And we have a relation between the pressure and the density. What is very important for the comprehension of Novae event is that an increase of the temperature, in case of an increase of the temperature, the volume will remain constant. Second important point, from a study of various models, I show a graph with, in abscissa, the mass of the white dwarf and ordinates the accretion rate, of matter at the surface of the white dwarf. It has been established that three different regimes can be observed, depending, of course, of the mass of the white dwarf. Above this curve, called accretion rate critical, we can observe a steady burning of the accreted matter from essentially proton-proton chain, which produces large envelope. Above this curve called accretion rate stable, the envelope will expand. Under accretion rate critical, the envelope remains degenerated and its volume remains constant. This is the field of Novae. The white dwarf accretes matter from the donor star via the accretion disk and forms an envelope at the surface of the core of the white dwarf. This envelope is very thin, about 10 kilometers. for a global radius of about 10,000 of kilometers. The pressure has been established from various methods, and the pressure is proportional to the mass of the white dwarf and the mass of the envelope. The pressure with the accreted material will increase until what is called a critical pressure, very high pressure, and from this pressure, the nova event will happen. The accretion during tens, hundreds, thousands of years with a very low weight forms the envelope. Huh? Sorry. During this phase, it is possible, but not sure, that there is a mixing from the core of the white dwarf and the envelope. The temperature is high, sufficiently high, about 10 million degrees, that the proton-proton chain nuclear burning can produce energy. As the material is degenerated, there is a slow increase of the temperature, but the volume, the height of the envelope remains about constant. Part of the energy, and this is the reason why the increase of the temperature is very slow, is transferred eventually by radiations, but also by electron motion. Just before the nova event, the release of energy by produced by the PP proton-proton nuclear burning will increase, and the temperature increases. Thus will produce the thermonuclear runaway, thus in fact instability of the production of energy. This is the onset of the convention, and we observe, no, we don't observe, sorry. The models propose that we happen the convection in a very thin layer just at the surface between the core of the white dwarf and the envelope. The temperature increases so much that the proton-proton reactions are replaced by CNO cycle. In the first time, by the so-called cool CNO cycle, which is much more energetic than the proton-proton reactions. The second time, the models predict that the convection in the envelope reaches the surface of the envelope, and the temperature increase. We are in the hot CNO cycle, which is much more energetic than the cool CNO cycle. The temperature of the envelope increases until it reaches the Fermi temperature. The Fermi temperature, which depends essentially on the density of the envelope, the material of the envelope becomes normal and reacts as a perfect gas. So the volume of the envelope increases for the first time since hundreds, thousands of years. Of course, due to the very high density of the white dwarf, the initial value of the expansion, the speed, is very slow, few tens of kilometers per second. After a few hours, the envelope, the radius of the envelope increases. The donor star is embedded in the envelope. The temperature decreases as a result of the perfect gas law. The luminosity increases a lot due to the large surface of the envelope. And the models show that the luminosity is near or above the Eddington luminosity, so it will produce an increase of the speed of the envelope. Note that the orbit of the donor star can produce variation of the speed of the ejecta, of the shape of the ejecta, and perhaps also from the Lagrangian point can produce some blobs and so on. At the state, we have a scale of about 1 million of kilometers. About one day after the beginning of the thermonuclear runaway, we have the release of the ejecta, but no model can explain exactly at what moment the ejecta is released. The speed of the ejecta becomes very high, from hundreds to thousands of kilometers per second. As the ejecta has now a very large volume, the temperature becomes very low, about 10,000 degrees. One key point is that only part of the envelope is released in the form of the ejecta. For the theoretical models that I have used for this presentation, with a white dwarf of 1 solar mass, it has been established that the ejecta is only 1/3 of the envelope mass. At one day, the photosphere is cool, the ejecta is optically thick, and we see the continuum, which mimics the continuum of, say, A-type star, with only Balmer lines, I1 2 lines. The ejecta is thick, so many of the metal lines are in absorption. Also, due to the composition of the outer part of the ejecta, we can observe P Cygni profiles. At the maximum luminosity, the envelope is at its maximum radius, about 1 astronomical unit. Temperature is very low, from 5 to 10 thousandths of kelvins. The ejecta is optically thick, and the photosphere is very near the surface of the ejecta. Few time after, the ejecta continues son expansion, expands, and the envelope recedes. As it recedes, due to the gravity of the white dwarf, of course, its temperature increases, perfect gas law. And it will increase, the envelope radius, yes, decreases, so the temperature increases until, say, 50 and even 100,000 of degrees. At this moment, the production of UV radiation is very intense. So we have also an increase of the ionization state of the different species of the ejecta. The ejecta, due to its expansion, becomes optically thin, and many radiations from visible to UV range can be observed. This is the phase in which the nova can be observed in ultraviolet and also X-rays as a super soft X-rays source. The ionization degree increases, and we can observe very ionized lines, such as I17 or I110 and more. At a certain moment, there is the turn off. The thermonuclear reaction stop. We have formation, the new formation, the formation of a new accretion disk, and the system will produce from the accretion many dwarf nova outbursts until the next nova event in thousands of years. It has been a pleasure to study this nova Delphini 2013 with many astronomers' telegrams from the spectra obtained by the group and many publications. This nova has been the first nova observed in gamma rays and second classical nova observed in gamma rays. Our observations have been used for publications in science about gamma ray production by Novae, but also in a publication published in Nature, which is the first publication using interferometry showing the real development of the ejecta of a nova. The scaling of the fireball phase of the nova has been obtained using spectra obtained by our group and especially Olivier Garde. And this is the content of the publication of Nature. Often, one can see in the various publications the usage of I12 and helium, nitrogen types of nova. The idea has been were developed by Williams in several publications at the end of the 20th century, and he proposed classification between I12 novae with lines with low velocity, especially I12 lines, P Cygni profiles, and this is often observed in slow novae. While in helium nitrogen novae, we observe at the maximum luminosity broad lines of nitrogen, of helium, and so on. So this is the first taxonomic classification. But behind this classification, there is also, in the spirit of Williams, models of the ejecta. For the second class, helium nitrogen novae, Williams thinks that this is a single ejecta, very fast ejecta that produce this kind of profiles. For I12 novae, he considers that there is first a single ejecta, and after there is a wind from the remaining envelope of the dwarf Novae. Sorry. Steve Shore disagrees with this model and considers that there is only one ejecta and that all the observations of the variations of the spectrum of the nova is the result, in fact, of opacity on the various ionization stages. And he has produced with Elena Masson, some models of the ejecta. The synthesis, perhaps me, I don't know. Just before the last part, just table of the various kinds of nova that can be observed. Traditionally, we consider that classical nova has been observed as a nova only one time, and recurrent novae have shown several nova events during the last century. The classical novae can be really classic, produced by cataclysmic stars harboring main second star, or by symbiotic stars, which produce very slow outbursts. Symbiotic stars harbor a white giant or a Mira star. The last one is very interesting because we are studying it with colleagues in Australia. The recurrent nova are classified in three types. The last one is the symbiotic recurrent nova class, with notably TCRB and RS Ophiuchi. TCRB is very interesting because Bois-Schaeffer has recently showed that the current light curve, here is dots, blue dots from AVSO database, follows exactly or almost exactly the same luminosity curve than in with this line, the nova event which occurred in the middle of the 20th century. So the prediction is that in a few months or years, 2 or 3 years, we can observe a nova event in TCRB. A spectrum of the symbiotic nova CNCHA obtained by Colin Eldridge in Australia shows the very nice emission line spectrum of a symbiotic nova. Now, conclusion. I have shown the typical light curve proposed by McLaughlin, but it appears that the reality, this is the typical light curve. The reality is that the light curves of nova can differ a lot, and notably, some of the nova shows strong oscillations during their decline, or even a flat top at the maximum light. And this will be the conclusion of this part. Here is here are the luminosity curves of the two recent nova observed in the northern hemisphere with NovaCast 2020, with a very different light curve in comparison to the classical model, with a top level before the formation of dust and the decline of the luminosity to about 20 in B-band. Second one is somewhat different, but very interesting, showing flat top at the maximum luminosity and after some oscillations. Here's the spectra obtained by the team of NovaCast 2020 from low resolution spectra, and the study has been produced by David. He produced also from calibration of the spectra influx using AVSO photometry. This very nice measures of the flux in of the various bands. There are two books that you can download from my website, and I strongly recommend these two books about nova events. And another one about cataclysmic variables, which is very interesting, and also the Warner books produced in 1985. Well, I hope that all is correct for you. I have not seen the chat, but perhaps we can have
yes,
a break.
Yes,
we have a question. I have a question. How does the O1 and N103 flash that happen about 2.5 magnitude after the maximum brightness you mentioned work? What's happening in the nova at this moment?
Tu peux me le dire en français?
J'ai une question. Comment les raies O1 et N1 et O3,
oui.
Le flash, qui
oui.
apparaît de 2,7 magnitude après le maximum de... Voilà. Et qu'est-ce qui arrive dans cette nova à ce moment-là?
OK. Ça va être la deuxième partie.
Ah, it will be the next part. And another question, I think from Sean, what does a lower accretion rate lead to a nova, but a higher rate lead to a steady burning?
Yeah. Et la question, c'est?
Alors,
qu'est-ce qui fait que une accrétion lente conduit à une nova, mais une accrétion plus rapide conduit à steady burning? Je ne sais pas comment tout ça.
Oui, tout à fait. OK. Où est-ce qu'elle est? Come back. This one. Sorry, I'm a little bit tired. Yeah, this one. This is a question of equilibrium. If you have high accretion rate, the proton-proton thermonuclear reaction will produce so much energy that you have a permanent level of not exactly. The production of energy is so high that you have not the degeneration. The material remains normal. Here we have degeneracy, there no. There, the proton-proton chain produces energy which is dissipated from, I said, electron motion and radiation. There you have higher produce of energy, and the envelope remain normal. Is it sufficiently clear? I don't know. I propose.
He says thanks. I think we have a last question for this first part from Matthias. Where does the iron come from? Iron in iron Novae during hot CNO cycle or due to high metallicity of the companion?
Yeah, second.
The second?
The second was the second point is correct. Yeah, we have no production of iron. Iron will be produced only on very higher
temperature
energies events such as supernovae. And this is only the iron accreted from the material of the donor star. About this question of first question, I propose will propose on more better response on the forum.
Okay. So, well, we also have a question from John Whitmore. At the extreme temperatures of the envelope at maximum, is this where heavier elements above the iron are produced, or is this the only possible in supernovae? This is what you said. I think we don't have heavy elements produced in novae.
It's only the synthesis of new elements is only from the CNO cycle.
Okay, so there is nothing else than that.
No. Essentially oxygen, nitrogen, eventually a little bit fluor, but
well, Novae is a small player.
Not higher, yeah.
Okay, wonderful. I propose that we have a quick break and we take 5 minutes, 5-10 minutes maximum, and we come back for the second part, which will be more practical. Okay.